Hello, student. I hope you are doing well, and I'm very happy to welcome you to today's class. As you are aware, in this chapter, we have been studying systems of linear equations and using matrices to solve those systems. We have already done that using the augmented matrices and the Gauss-Jordan elimination method, the row reductions in the first two sections. But we never studied the matrices as objects in themselves, right? We used the matrices, but we did not study the matrices themselves, which will be the goal of today's lecture. Okay. So what are matrices and what kind of operations can we do on them? Like we add real numbers, 2 plus 3 equals 5. Can we do something similar with matrices? Can we multiply them? Can we divide them? Is there a reciprocal of a matrix and so on, right? All these questions. Okay. um, Having and working understanding and skill to operate on these matrices will go a long way in our ability to use them successfully when it comes to their applications, right? Plus one more thing I should add, not just for solving equations, the matrices themselves, as it turns out, can be can have their own independent applications in real world, as we will see with some examples in the maybe at the end of this lecture or in the next video where I will be solving the problems. Okay, now let me begin. The outline of today's lecture is this. We will look at the definition, we'll look at what are row, column, and those matrices. And then we start looking at operations, adding, subtracting matrices, multiplying a matrix by a number, and then we will go to matrix multiplication towards the end, as you can see, because the matrix multiplication will turn out to be the most complicated one usually. Okay, and then we will look at the definition of identity matrix and what it means to write a matrix equation for a system of equations. This will be different from the augmented matrix that we did earlier. Okay, so there are two things here: matrix forms and matrix equation. The augmented matrix was a matrix form of the linear system. Matrix equation would be an equation involving matrices themselves. Okay, more on that as we go there, reach there. Okay, definition of a matrix. Any rectangular array of numbers. How simple is that? Okay, so as you might have already, with your experience, you put numbers in a rectangular block, that is a matrix. That's it. Okay, but that is just a pure mathematical definition. What do those numbers represent? That is up to us. In a real world application, those numbers will represent different things. Basically, the rows and the columns would stand for some things. Like in the augmented matrix, each column was the coefficients of one particular variable, right? So they will have meanings, but the matrix itself is just a block of numbers. And so we talk about the size, right? There is a small matrix, there is a big matrix. How do you identify? We talk about something called size, which is also called dimensions, plural, okay? Because there are two things, rows and columns. You call it dimensions or order. All of these are synonymous words. In some context, people want to distinguish between the number of elements versus the dimensions, then you might use a different, the size might have a slightly different meaning than dimension. But in general, all of these are used synonymously. Okay. The order of a matrix, size of a matrix, dimensions of a matrix. What is it then? All of these refer to the what tells you exactly the shape of the matrix, right? The number of rows and number of columns. For example, if I write a matrix like this, I wrote random numbers, okay? Now it has two rows, as you can see, and three columns. So you would say this is a 2 by 3 matrix. That is read as by, okay? 2 by 3, the cross sign is read as by, 2 by 3 matrix, okay? And then there is a question of how to refer to individual elements within the matrix, okay? Let me do one thing. To create a distinction, I'm going to change some of these values to negative. Okay, now all six numbers are different in that. So if I want to point out, what number, where in the matrix is that number 5? This is needed for communication, right? If I have to explain to somebody to where to go and look, there should be a systematic way to do that, right? This is like coordinate systems, okay? And it's very easy. First row, second row, top to down, first column, second column, third column, left to right. Now you see that number 5 is second row, second column, right? So you just say that is A sub 2 2. The subscript will refer to the position, the row first and column next. Okay, the first two is for the row, second two is for the column. So A sub 2 2 is 5. Okay. Now let me give an example where the row and column numbers are different. Okay. And that would be, for example, if I want to identify -1 by its position. Okay. I would say when I write A there, typically it means I'm naming my matrix as capital A. Okay. Then I use small a to refer to its elements, the position of its elements. Okay. A sub first row, third column, right? 1 3. That will be -1. Okay, and so on. You get the idea. um, Two matrices are equal. Now when do you say two matrices are equal? Now a matrix is not just one number, right? It's a block of numbers. You would now call two of them equal if they have exactly the same size and their elements are also exactly the same in the same positions. Okay, so for this idea here I will give a small example here. Suppose you have 1 2 3 and 4. Okay, that is equal to, of course, 1 2 3 and 4. That is the only way. Okay, there is no other choice. What is not equal to? On this side I will say not equal to, say 1 2 3 4. Okay, although they have the same elements, their first two matrices here on the left are not equal. Why? Because, let me zoom in there, the element here, the first row second column element is 3. Over here it is 2. Just because all the elements over, in total all of them are same is not enough. They need to be the same entries in the same positions, in identical positions. Okay, that is the meaning of the word corresponding. When we say corresponding, it's the same row and the same column, and it should be for all of them. Like out of, let's say there is a big matrix, with 10 by 10, like 100 entries, 99 of them match and one doesn't match. You don't say they are equal. Okay, they're still not equal. So all, here the word is highlighted, word is all. All right. So basically exact copy of itself is equal to it, otherwise not. Okay. So here is example from the slides in the book. This is a 2 by 3 matrix, as you can see. The entry A, okay. There's also this convention where people separate them by a comma. Okay. And that you might have to do specially if you have big matrices with, let's say, 12 rows and 3 columns, right? So if I say A, 1, 2, 3, it will be difficult to understand, you know. So you might want to distinguish them by putting a comma. So it's the 12th row and third column. But for small numbers, sometimes we just skip the comma when it is clear in the context. Okay. Now in this example, if we simply wrote 1, 2, it would not be a confusion. Okay. Keep that in mind. So 1, 2 will be the first row, second column, right? That's the negative one here. 2, 3 would be second row, third column. And these two matrices, as it's, you see exactly corresponding entries, they are equal. Here, this is another way the matrices will not be equal, by the way. Okay. Again, you see the exact same entries. You might even say, the 372 and 372, they are in a sequence. The problem is the dimensions themselves are not equal. On the left side, it is a 2 by 3 matrix. On the right side, it is a 3 by 2 matrix. Okay, they are not equal. So that those are matrices in general. Some matrices are special, right? You have names for them. A column matrix, a row matrix, and a square matrix. And the names are self-explanatory, I would say. Okay. A row matrix has exactly one row. Like, you just put the numbers in one row. That is a row matrix. A column matrix has only one column. So only one entry in a row, basically. Every row has only one entry, and so it becomes a column. Okay. Square matrix has equal number, like 1, 2, 3, 4. 2 rows, 2 columns, 3 rows, 3 columns, or 1 row and 1 column, extreme case, right? Equal number of rows and columns, square matrix. Here is example. This is a square matrix, that's a row matrix, that's a column matrix. Okay. You see it once, you hear once, and you remember it. Okay. Those are those kind of definitions. Okay. Now the operations on matrices, right? Adding and subtracting. These two are very, very intuitive, and if you guessed how you would add two matrices, you will be correct. Okay, your guess is the correct guess. So I'm just going to write here. Let's say 1, 3, minus 1, 4, 2, 3. And I want you to do this operation. Okay. I should have started a little bit on the left. I seem to be a little bit poor in this direction. Okay. And let's say 3, 4, 2, 5, 1, 0. You think what is the most logical way to add them? And I'm telling you, you will be correct. Okay. Did you do this? 3 plus 1, 4. Here and here. Then you took this 3 and this 4 and you added them. That became 7 here. Then you took this minus 1 and this 2 and added them. That became 1 here. Similarly, 4 plus 5, 9. 2 plus 1, 3. 3 plus 0, 3. That is matrix addition. Okay. And the word is here. Corresponding entries. That immediately means you cannot add if they don't have the same dimensions. Okay. Two matrices of the same size. Two matrices. First of all, they can only be defined if they have the same size here. Otherwise, you cannot add matrices. Okay. That brings me to one of the questions I was posing earlier. We do additions of numbers, right? Does the addition of matrices work in a similar way? The answer is the addition of matrices works in a similar way, but only when their dimensions are equal. Okay. Similarly with subtraction. Okay. And the last one here is not defined. Some more examples. In the subtraction, be careful that you have to subtract the second matrix and you have to change the sign. Okay, so I will illustrate with the first entry here. There is 2 here, there is -1 here. When you subtract 2 minus -1, will become 2 plus 1 and result is 3. Okay. Okay. Now we look at a matrix multiplication of a special type, not the general type. The special type is you take a row matrix and multiply to a column matrix. And how is that done? This will be a precursor to general multiplication. Okay, the reason we are studying this here is once you understand how a row is multiplied to a column, this is done repeatedly when you multiply two matrices with more number of rows and columns, general matrices. Okay, you do this row times column repeatedly in a certain pattern. So this is like breaking down the whole process into bits, so it is easy to understand. Okay, and I like this idea. So first, what is multiplying a row with a column? The addition and subtraction I was saying is easy. The matrix multiplication is a little tricky, right? It works like this. You multiply this big row with big column like n. So that could be like 10, 10 entries or 100 and 100 entries. Okay, a huge row and a huge column. But when you do that, you end up with one number. The result is just one number. And what is that one number? That one number is the sum of these products. A1 with B1, A2 with B2, and so on, right? Ultimately, AN with BN, and then you add those products. That is the product of that row with that column. Okay. So firstly, it shows, this is a definition of how to multiply. But immediately again, you see that you cannot multiply a row with a column if they don't have the same length. If the row has 3 elements, the column must have exactly 3 elements for this multiplication to make sense. Okay. So what is important here is 1 cross n row, right? One row, n number of entries, so the n number of columns, and n cross 1 column. There are n rows, only one column. That will be n cross 1. When you multiply them, this vanishes. The result is a 1 cross 1, 1 by 1 matrix, which is basically just a number, put it inside the matrix brackets. Okay. And this thing that you noticed here, that you get rid of this number of columns from the first left side and number of rows from the right side, is what will happen in general matrix multiplication as well. Okay. Here is an example. You multiply that with that. So you multiply 2 with -3. You multiply -1 with 2. And you multiply 3 with 5. And take the sum of all of that. The result is 7, the product. Okay. And here there are 4 entries in the row, only 3 entries in the column. It's not defined. All right. Now the matrix multiplication. Okay. If you have a m cross n matrix and another n cross q matrix, you can then multiply. And as I was saying earlier, the two things will vanish. You will get a product which will be m cross q. Okay. M by q matrix. Okay. And the logic, then okay, that is the dimension, but then you will ask what are the values inside, in the product. And the answer is, in the product, if you are looking for, let's say, second row first column, okay, second row first column, suppose you are looking for this entry, that would be obtained by taking the second row from the left side and the first column from the right side and multiplying them like we saw in the previous page. Multiplying the ith row and jth column will produce the element a sub ij in the product. Again, so something, so if you remember this logic, like it's so nice that you can immediately apply it. Okay, first row and first column will produce the first row first column element in the product, and so on. Example will be much better than me explaining in words. Okay. Look at the matrix multiplication of a 2 by 3 matrix with a 3 by 3 matrix, right? So according to our uh, understanding so far, this would disappear and your product will be a 2 by 3 matrix, first of all. And this is crucial, okay? Always make note of that first. What will be the dimensions of the product matrix, because that will help you stay on track and do the correct multiplication. Okay. Now, how does it work? 2, 3, 2 minus 1, 3, first row times first column. Okay. And I'm going to detail that multiplication on top here. So it will be 2 times minus 3 and plus negative 1 times 2 plus 3 times 5. Okay. Row times column. And that gives you negative 6, negative 2 plus 15. That is 7. That's your product there. Then what we do, move to the, you can like move to the next row or move to the next column, but like fix a pattern. Okay. What I will do is, I'll keep the same row, go to the next column. So I will be multiplying the row, first row 2 minus 1, 3 with the column 2, 1, 3 by the same pattern. Okay, by using the same technique that we just did. And that will go where? Here, 12. Because that 12 here is first row, second column entry. And it is obtained by multiplying the first row with second column. Will be here. Okay. And repeat that, you get your entire product. Practice it. If you do this, copy this on your notebook and complete the multiplication on your own and check your answer, you know immediately you have grasped the idea. Okay. Moving on. Here you have a 3 by 3 matrix on the left and you have a 2 by 3 matrix on the right. And from what we know, these two are not equal. So not compatible. The product is not defined. In other, we say these are not compatible for multiplication in that order. By the way, those are the same matrices. Did you notice that? Okay. So what happened here? Not only that you saw when it doesn't multiply, you saw one more thing. It is possible AB exists, BA does not exist. In matrices, that is possible. Now that in that way, you see the multiplication of matrices is different from how we multiply numbers, real numbers. In real numbers, you can always multiply either way and they will be equal. Now, in matrices, you may not always be able to multiply both ways. Okay. I'll talk about one more aspect of this idea one in a second. Let me just write the main sentence on top. Matrix product is not, this is the word, okay, commutative. When two products are equal from both directions, AB equals BA, that property in general, in matrices, in numbers, in polynomials, that is called commutative property. Okay. From our prior experience, we know numbers are commutative, polynomials are commutative. If you have two polynomials, px and qx, and if you multiply them in whichever order, they will end up in the same polynomial at the end, right? But we have seen one example here. I don't know, I can't recall if there was any other example that you might be introduced prior to this level of mathematics, where the product is not commutative, except if you studied vectors. Okay. Um, Vectors product is not commutative. That's one example. The the cross product type. In there also there are different types of products. But mostly not. Okay, so this would be the first time you are seeing something strange, right? That multiplying, in the reverse order may not result in the same thing. Now, I was saying I'll come to one more idea here. In this example, they are not equal. They are not defined, right? You could not multiply BA, so there is no question of equality. What if they were defined both ways? For example, I will give you, if A is a 2 by 4 matrix and B is a 4 by 2 matrix, suppose, okay? First you do. Tell me what will be the dimension of AB and what will be the dimension of BA. Okay. And write your answer and check with me. And you did it correctly. AB is 2 by 2. BA is 4 by 4. So obviously they're not equal. Okay. So even when both products are defined, they may not have the same dimension. Number one. That reminds me one more. Okay. And I promise after this I'll move on. If A is 3 by 3 and B is also 3 by 3, then AB and BA will also be 3 by 3. Right? All of them will be 3 by 3. In that case, will they be equal? The answer is still not guaranteed. Okay, I'll write that here. AB equals BA, not necessarily. Okay. And hopefully in your exercises or somewhere in the slides or our work problems, we will get an example for that. So in any case, the product is not guaranteed to be commutative. They may be sometimes. We're not saying they will never be. Okay. But in general, not. Okay. Moving on. Identity matrix. Like, in any new system of objects, some objects are special, right? In numbers, 0 and 1 are special because 0 is what we call the additive identity. Now, I'm trying to, recall your school arithmetic knowledge and connecting that here. Okay, 0 is the additive identity. Why? Because you could add 0 to anything and it won't change the identity. The identity of the other number, right? The x will be preserved, we say, right? So 0 is the additive identity. Similarly, 1 is the multiplicative identity. You could multiply by 1 and the value will not change. It preserves the identity of what it is multiplied to. When in matrix we have a similar matrix that is called an identity matrix, but this is the multiplicative identity matrix. We just call it identity matrix. It is the multiplicative identity matrix for your understanding. Okay, nobody says that. It is accepted definition that identity matrix is the multiplicative identity matrix in the context of matrices. Okay. Now it no you can easily see. Okay, I'll not get into too much details here. If you want a matrix which when you multiply and does not change the original matrix, it has to be a square matrix first of all. Because if your original matrix is like 2 cross 3, you multiply with some matrix and it should not change the matrix. So the dimension should not change. What is the only way? It has to be 3 cross 3. The first number has to be 3 because only then you can multiply. The second number, the number of columns has to be 3 so that the result is again 2 by 3, right? That should not change. So the identity matrix has to be a square matrix. And because of the way matrix multiplication is defined, it turns out the diagonal entries have to be 1, 1, 1, and the rest of them have to be all 0. It can be proved, okay, why this has to be the identity matrix, but nobody does that, okay. I mean, nobody does that in a specific in a finite mathematics class. But you can appreciate why that is the case. Okay, that will help you to remember the matrix multiplication also. Each of this entry here, for example, the second entry here has to be 1 because that has to multiply with the same position entry in the other matrix, in the other 3 by 3 matrix. Okay, it has to multiply with that entry, and one time that number will produce that number and will stay there. So that number will stay as it is. And the other numbers would have been, the other values are 0. So it doesn't change, whatever that number was will not change because the rest of the products will be 0 because these things are 0 or because these things are 0, whichever way you see. Okay. So identity matrix will be now defined like this. Matrix, square matrix where diagonal entries are all 1, rest of them are 0. Okay, and what is the property? I'll write that in equation here. A times I or I times A will result in A, like the number 1. Okay, then you might wonder, is there a parallel of the additive identity? And the answer is yes. The parallel for the additive identity will be the zero matrix, what we call. Let me see, it's not probably covered here, so I'm going to write. Zero matrix is similar to the number 0 in real numbers. So what would be a zero matrix? Whatever matrix you have, if it is a, let's say, 2 by 3 matrix, then the zero matrix for that matrix will be a 2 by 3 matrix with all zeros. So it is not just one matrix. Okay, by the way, even the identity matrix is not one matrix. It depends on what order you are dealing with. If you are dealing with 2 by 2 matrices, then the identity matrix is 2 by 2. If you are dealing with 3, then it is 3 by 3. Whatever you need in order for the matrix multiplication to be defined, that order, okay, square matrix. Similarly here, zero matrix. So in general, we say zero matrices. No, there are so many zero matrices of different order. Okay. Moving on, you can actually do this multiplication and verify. Again, a good exercise to do. Okay. And also it will help you practice the matrix multiplication. Do that multiplication, you check that the values do not change. Whether you multiply from the left or you multiply from the right, whichever side you multiply, it doesn't change. And here's what I was telling earlier, I times A equals A times I equals A. Sometimes we write this subscript to indicate the order of the matrix. Like I sub 2 will be 2 by 2 matrix. Okay, finally, in this slides, in this lecture, we are not going to be doing too many examples of solving the equations, we will just go run through one example, but you get introduced to the idea, okay? This concept of matrices and matrix multiplication now can be used to solve equations. How? You can first of all convert a system of equations into this form. We will look at an example how it is done very soon, okay? Once you do that, okay, if you are able to find what is called an inverse of this matrix, if it exists, and all of that is coming up soon, okay, then you multiply by the inverse on this side, that is like the reciprocal conceptually. So A inverse and A will cancel. You multiply the same thing on that side also, then you will be left with x equals A inverse B, right? So we will be able to solve this x would be the variables, like the values of x, y, and z that you want to find. So this is the concept. Okay, you convert a system of linear equations into matrix form like this. This is called the matrix form of the system. And then you find the inverse and multiply on both sides, and you are able to solve the system. Okay. And how it is done? By taking the coefficients and all of this description. Let us look at the example, which is easy. Okay. Look at the system of equations and don't look at the solution below that. I'm going to cover it in fact, and let us write it and we will check them. Okay, it's very easy. What you do, you take the coefficients first. Okay, 4, -7, -3, 2. Right, coefficients of x, coefficients of y. Just like in augmented matrix, if any variable is missing, you write 0 there, for its coefficient. Now this is interesting, okay? This times x and y in a column. Why would we do that? Because now if you remember the matrix multiplication, if you multiply these two matrices, you will have to multiply this row with this column, right? So you would be doing 4x plus minus, in this case, 7y, right? That is your left side. The right side of the matrix would be put that those numbers in a column. Okay, and when you multiply on the left side, you get 4x minus 7y, and correspondingly on the right side, you have 9 and -5. So basically, this first entry here should be equal to first entry there, which is the given equations, right? So this is basically a way to rewrite the linear equations in the matrix form using the concept of matrix multiplication. Okay, and let us see how it was presented in the book. Okay, so equation 1 is the first row, equation 2 is the second row, and that is one concept. Second concept is the variables. Okay, the numbers that you write there, those are the coefficients of one variable each. Okay, coefficients of x in the first column, coefficients of y in the second column. Constants on the right side as a column. Okay. As I said, later we will be using this technique to solve the equation, which will be our future agenda, the next video. Here is a summary of what we discussed, okay, about the, when you can add them, what is the meaning of matrix, and how to get the product element when you multiply two matrices, and then it has its applications. In the next video, I will work through problems on this topic, operations and matrices. Okay, see you there. Thank you.